Right. Tutorial time. So, where would we start? Come on. Where would we start?
Conservation of energy, question 10.
Yes, you have some from conservation of energy. Well, first, before conservation of energy, working power. Anything from that?
What is an incline of 1
Is that the last one?
Yeah.
I told you that's for fun. You're to find it online yourself. It's okay later.
I think that if you depends if you start long, the light income, if you get, once you get that, then it works out.
Hugo will show you how to do it after class. For fun.
What is the incline of?
Oh, he'll tell you after class. He knows exactly what it is, don't you?
Yeah.
You remember?
I remember.
Yep.
Okay.
He'll help you.
Is it annual or?
Yep.
Yeah.
He will tell you everything very true. So we'll leave that one. But what about the next one? Then the conservation of energy, you said you had one. 8 and 10, yeah? I'll do 8 and 10. This is 8, yeah, and this is 10, yeah. 8 is the sign, isn't it? Incline.
Oh, the incline, yeah.
Sign. Yeah, sign actually, yeah. Alright, let's have a look at conservation of energy. So this one here, okay, conservation of energy. Question 8 and 10. Louise, do you have anything you need to see, or you just want 8 and 10, or say, or both, or everybody? I'm going to do 8 and 10. Fair enough, yeah? 5, 6. Well, what did you do, Louise? Tell me what you did.
I drew 1, 2, and 3.
Yeah? And what happened for 4, 5, and 6, 7, 8, and 9, and 10? You couldn't do them, or you didn't do them?
I wasn't so happy.
Oh, okay, then I'll just say so. So, 1, 2, 3, 4, no problem? Or 1, 2, 3, no problem?
Then actually 1, 2, 3, 4 is no problem.
Is a problem?
No problem.
No problem. So start from 5? Okay, from 5. So, 5. A girl throws a rugby ball. Listen, a girl throws from 5, sorry. A pendulum 1.3 meters long swings, so its greatest angle is that. Find in terms of G its greatest speed. Okay, so what you have is, you have this pendulum. Its length is 1.3 meters. And it starts here. And it swings down to here. And I want the speed here. And they give you the A. They tell you that tan A equals 5 over 12. What's the A, please? Can you do tan inverse 5 over 12? What's the A? Huh? Yeah, I know, but in physics we're allowed to. So it's good for us. So what's the A? 22.6. Okay, great. Now, what we can say, is that potential energy here must equal the kinetic energy here. So now we need to find the height. Yes? So, let me see. If this here is 1.3, then this is 1.3. This piece here is, and then we have this piece here. This piece here is 1.3 cos A. What's that, please? 1.2. Perfect. So then how big is the H? Yeah, 0.1, because this is here to here, 1.2. So we have M, G, H equals a half M V squared. that means GH equals a half V squared. So that means V equals square root 2GH, which is square root 2 multiply 9.81 multiply H, which equals...
So they want it in terms of G.
Oh, do they? Alright. So what's 2 multiply... Oh, so it's square root 0.2G. Is that the answer at the back?
Yeah.
Oh, perfect. No. Yeah. 6 now? Yeah, 6 now. Okay, so I'm going on to 6. A tennis ball is hit into the air from 0.5 above the ground at 14 meters per second. Find the greatest height of the ball will reach above the ground. And it's hit straight up in the air. That's important. So you have it here, and the person is here, and it starts at 0.5 meter. Here's the ball here. And then it goes straight up, and then it falls back down. They want the height at the top. At the top, is the ball moving at the top? No, it's not. It's at rest. So what type of energy does it have here? It's only potential. And here, potential plus kinetic, because it starts off the ground, yeah. And we're given the speed is 14 meters per second. Okay, so again we have the potential energy at the top, which is mgh, equals the potential energy at the lower level, which is mg 0.5, plus a half mv squared. Like this. So, cancel, cancel, cancel. H equals 0.5 g. What's 14 squared divided by 2, please? Anybody?
98.
Thank you. And I divide by g because I have a g here. So I have H equals, do we have the number there?
10.5.
10.5?
That's the answer.
Yeah, for the H.
Oh, you just want to find out.
Yeah. Is it 10.5 here?
Yeah.
Okay, thank you.
Actually, I can cancel the G.
Yeah, what I did was I divide both sides by G, so that cancels there. That's why I have only H.
And then how to get the 10.5?
Ah, just put this on the calculator, because G is 9.8.
Oh.
Yeah. Yeah? Happy enough? Yeah. So next, 7. So 7 here, you have a bobsled slides down a frictionless surface which is at an angle 30 degrees. It starts from rest and travels 20 meters. So it starts here and then it travels 20 meters and it finishes here. How big is this height? This would be 20 sine 30. The potential energy here equals the kinetic energy here. So we have mgh equals a half mv squared. Cancel, cancel, so I get 40 g sine 30 square root, that's the v. Whatever that is on the calculator, what does it work out as? 14. A small ring, okay. A small ring is threaded on a smooth piece of wire which is bent to form a circle. Radius 5. The ring is projected with speed 14 from the slowest point, so vertical. Find the speed of the ring when its height is the same as the height of the center of the circle. Show that the ring will just reach the highest point of the circle when it comes to rest. Okay, now that's a little tricky. So let's have a look at 8. I'll draw it for you. So, can we look at 8? We have this ring. And there's a small ball here. And this ring here, its height is 10 meters. And they want to know if you hit the ball. Oh, sorry, the ball is hit at 14 meters per second, and the ball will go around until it gets to here, and it will continue. But they would like to know the speed here. That's what they want. They want the speed. What type of energy does the ball have here? And what type of energy does it have here? And kinetic. So the kinetic at the start is a half mv squared equals the potential plus kinetic later. So that's mg, what's the height? 5. Be careful because the 10 is to the top. They want it to the middle. Plus a half v squared, which is the v squared is what they want. So we can cancel the n's again. Is this 98? 5g plus a half v squared. Okay, so we have 98 minus 5g multiply 2 with a square root. Okay, you get that for v when you rearrange it. Take it over, bring it up, yeah. What's that on your calculator? Exact? Close enough?
9.997.
10 it is. Now the second part. Yep. Oh, because m is in every term. See, m. So you divide m in everything.
Sure, I'm not sure how to get the second.
No? Show me what you typed. Oh, here.
I can ignore the G.
Oh, no, you can't. Definitely not. 2 bracket 98 minus 5g. Remember, g is 9.8.
Oh, yeah, G is
Oh, you did? Oh, tut. Okay, let's see. Yeah. Oh, yeah.
What was it?
9.9.
Yeah.
Fine.
Thank you.
Okay, there's a second part which says, show that the ring will just reach the highest point. Okay, can I go down? Yeah. So what we want to do, the ring starts here, okay, and it goes all the way to the top. And we want to calculate the height. And we want to make sure the height is 10. In other words, we want to make sure that here, all the kinetic energy here gets changed into potential energy here. Yeah, I should actually say something here in the question. Whose is this? Yours? Yours? If you look here in number part 2, show that the ring will just reach. See what it says there in part 2? Show that the ring will just reach. Can you underline just reach? Underline that. The meaning of these two words is no velocity, no speed at the top. Just reach means when you get to the top, you have no speed. Okay? Did you know that? No? Yes? You did? Really? Good. So just reach means you just have no speed at the top. Okay? Right. How's my battery doing? I'm okay. So a half mv squared equals mgh. Let's see what the h is. So h, 9.81. Well, in this book they use 9.8. H is 98 over 9.8, which is 10. Yeah. So 10 is the highest it can be. It's the maximum height. Okay. Scroll down. 9. A smooth circular wire radius A is fixed in a vertical plane. Small ring. Okay. Right. So 9 is very similar to 8. In number 9 you have a ring, and here is A, and here is A. Well, I know some people know this. Who knows what the name of this part of the circle is? What do we call this part? I know some people know this, so I want to know the non-native speakers. What's the name of this part of the circle? This part is called what? Do we know? Huh? Say again? Oh no, the diameter is the full length. What's the half of it called? Radius. Yeah. So we call this part here, this is called the radius. The radius is equal to A.
Just half.
Half of it, yeah. Here, it's fired. And we're told that the speed u is equal to root 2ga. This is the speed at the start. So the first question, part 1, is what is the energy at the start? Okay, what type of energy does it have at the start here? Just kinetic, isn't it? Not potential. So that's a half mv squared. That's a half root 2ga squared, which is a half 2ga gone, which is m multiply g multiply a. That's the first part. Now for the second part, what happens is the ball goes up, and then at some point it stops, and then what happens is it falls back down. They want to know what is the maximum height. So what's special about the ball when it's up here? Well, it's not moving. Does it have kinetic? No. It has only potential. So we have to do potential energy equals this kinetic energy at the start. So we have mgh equals mga, because remember we did this already for the start. Cancel, so h equals a, yeah. So the maximum it can go is around about here. This looks like it when it's a. It'll only go halfway and then fall back down. And what they'd like to know to finish it is how fast is it going when it's here, halfway up, when its height is a over 2. A over 2. So again we have the energy at the start equals the energy at the end. What type of energy does it have here at the end? What energy does it have? Does it have kinetic? Yeah? Does it have potential? Yeah, it does. It has both. So we get mGa equals a half mv squared plus mgh, the height. And they tell us the height is a over 2. So, m's all go. So we get, I'll multiply by 2. So I get 2Ga equals V squared plus Ga. So 2Ga minus Ga is Ga. I take this over. And I square root. The answer is square root Ga. So they do get more difficult as you go through them. There's still 10 to do. Yeah. I'm going to do number 10 now. So Ibrahim, was number 10 your choice, was it? Yeah. Who, did you do number 10? No. Is the difficult part the language or not the language? Okay. Let's have a look at 10 now. Yep. Did you do 10? Okay, let's see what happens in 10. Battery is okay still. Right, 10. You have this is called a seesaw. And Johnny is here. And Margie is here. Margie is bigger than Johnny. So Margie is mass m and Margie is mass 3 over 2m. Margie, whose mass is that, then sits on the other end, which is a half a metre off the ground. So we're told that the height here is 0.5 meters. Right. So what happens when Margie sits on the seesaw? What happens? Oh, Johnny's got ground on it, so I should have drawn this going at an angle more. Let me redraw him. Okay. So yes, look, I'll even have grass and everything. So John is on the ground. What happens when Margie gets on the other end? Well, it goes up. Okay. Now, at the moment, Johnny's energy equals 0 because he has no kinetic energy and no potential energy. What about Margie? What energy does she have? Yeah, she has potential energy, doesn't she? Which is equal to mgh, which equals 3 over 2 0.5, thank you, which is a half, and sorry, and I forgot my g. So mgh is all there. Or in other words, 3 over 4 mg. That's her energy. So in total, the energy at the start, this one plus this one, is 3 over 4 mg. Now later what happens is they swap, don't they? Johnny's going to be up in the air and then Margie's going to be on the ground. So later, what type of energy does Margie have? Well, she has only kinetic energy because she hits the ground. And what about Johnny? Isn't it when it hits the ground, isn't it? Yeah. What about Johnny? potential and kinetic. Yeah, because when she is falling, he is rising. So when she hits the ground fast, he goes up fast. So he has kinetic and potential later. So he has kinetic and potential. Okay, I better get my charger in a second. So his kinetic energy is a half m. What's his m? It's just m, isn't it? V squared, and his potential energy is mg. And what's the height? It's a half. That must, and then we have Margie's energy, it's kinetic, a half m v squared. So in total the energy at the end equals a half m v squared plus a half mg plus 3 over 4 mv squared, if I add these two answers together. But the energy at the start must equal the energy at the end. Here is the energy at the start, and here is the energy at the end. They must be the same. The energy doesn't change. So now we have 3 over 4 mg equals a half mv squared plus a half mg plus 3 over 4 mv squared. Okay, try to get the v. I'm going to plug my laptop in. Just try and get the v from that. Try to simplify. Make that simpler. No. Any luck getting the V for me? So, I should take this piece to the left. 3/4 mg minus a half mg, what's that? 3/4 mg minus a half mg is a quarter mg. And then a half mv squared plus 3/4 mv squared is 5 quarters mv squared. Now, what happens to the ends? The 4s? So I have g over 5 equals v squared, so v is square root g over 5, which is about 1.4. v is 1.4 meters per second. So that's how fast they are going. Yeah. Okay, what's next? So you might need to have a look at this. This is yours, isn't it? Yeah. So tell me what you need next.
Question 3.
3. Which one?
Conversion number. Then why most of the time producing coming
Just this part?
the second one.
Okay, so I'll do the whole thing. Yes. And what do you want to say?
Question
2. Okay. And Louise, what about you?
7 things.
Same size?
Yeah.
2 and 3? And what about you, Abraham? Which one? So 2, 3 and 4, yeah? Okay. Okay. 2. On the next page. Okay. Let's look. 2. So the A part, what is elastic collisions? You know who behind that? Yes, kinetic energy does not change, yeah, exactly the same. Alright, let's have a look at the B part. A block of wood, 2.3 kilograms, yes? And then you have a bullet here, which is 0.085 kilograms, and the speed here is 250 meters per second. Hey, listen up. So the question, first part, is when the bullet hits the block, look up please, look up. When the bullet hits the block, this will have a speed, V.
Yeah.
And then this will swing up here, and then it will swing up to a height, H. So for part 1, they want the V. Part 2, they want you to show it's not elastic, which I'm not so worried about right now. And then part 3 is they want the height. Okay? So this is what the picture looks like. Yep. And I am not going to do it. Tell me why I'm not doing it.
This is an example we did.
Yeah, it's the same as the example I did in class. So if you follow the example, I did one like this in class. In fact, I think I did one the exact same. I think I even remember the numbers. I think I went for 100 grams, 10 kilograms, 1 meter, and 200 meters per second. So because of this, I'm not going to do it. Sorry to break your hearts. So I'll go on to the next one, okay, number 3. Because number 3, that's the one with the atom, isn't it? And the 98%. So that one is difficult. I'll do... Yeah.
I tried to find
The V, yeah? It's different, is it?
this your example.
Yes.
Yeah, I put it here.
0.085,
Okay, and
250,
plus
0, equals, yes?
equal this number.
10.1. What's this 10.1 here? Sorry, that's the mass of the bullet and the block together.
Yeah.
So in this example, that would be 2.3 plus 0.085. So you should use that number.
Okay, because
That's the problem, is it? Yeah. So if you use this, then it's fine, yeah? Okay. So it's okay. I'll go to the next one then, number 3. Yeah? Do you want me to check what you did, Louise, for number 2? Or not? This one here? No, it's okay. Alright. 3 now. Okay. I'll start with 3B. So what you have is, you have uranium 238, and then a particle of mass 4 units is released. So it starts off like this, and then later you have this, and then there's a 4 mass leaving. So the question is, how fast is this going to the left? Is it? Yeah. Basically that's it, isn't it? Right, so we use momentum. What's the momentum at the start here? 0. Okay? Now, I need 2 V's. I call this one V1 and then I call this one here V2. There's 2. momentum at the start equals this momentum, we'll call these M's. I'm doing a little trick here. Remember when I did something like this in the last class? I called the mass of the proton, I think I just called it X. So I'll just call the mass of the protons and neutrons M. So I have 234 M's and then 4 M's leave. So anyways, 234 M V1 plus 4 M V2. What can I cancel? M's. So I get V2 equals minus 234 over 4 V1. Okay. Now this isn't me answering anything yet. What I'm actually doing here is part 2. Before I start part 2, part 1. Why is most of the kinetic energy carried away by the alpha? Sorry, I didn't give you the name. This one is called alpha here, and they called this one here thorium, wasn't it?
Yeah.
Okay. So they're asking me, why do you think most of the kinetic energy is in the small one? Yeah, I mean, it's not really a good reason. Yeah. This 4M is going really fast. So it has lots of kinetic energy. That's all. Because it's so small, it's like a bullet that's pushed out. It's like it's fired a bullet. So it has a lot of kinetic energy. That's all. That's all they want, okay? It has a lot of kinetic energy because it is released very fast. And you can even say it's like a bullet being released from a big gun. The bullet goes really fast and the gun just moves a little bit. It's the same idea, okay? The next part is more difficult. For this part 2, they want you to show that the energy here is 98% of the total, and therefore the energy here is 2% of the total. That's what they want you to show. And there's a couple of different ways to think about how you might do this. So does anybody want to give me an idea? How could we show that 98% of the energy is in the small mass and 2% of the energy is in the big mass? Well, my first question, what type of energy is this? Kinetic energy. Is any potential? No, because it's just like this. Yeah. So now we are asking, how can I show 98% of the kinetic energy is in the small one and 2% in the big one? Well, what do you think? What could we do first? Any ideas? Well, maybe the first thing would be to calculate the kinetic energies for each of them, right? So I should find out how much kinetic energy is in each of them and see what happens. So the first one, what's the kinetic energy? Kinetic energy is a half, what's the M here? 234 M, a half M V1 squared. And then for the other one, it's a half M, yeah, V2 squared. Yeah? Now, what do we think we should do next? But maybe before that.
Simplify.
Yeah, how to simplify?
Open.
No. Open what? No.
Substitute.
That's what Ugo's saying as well, yeah, before that. Well, look, before we do anything, we need to try and understand what we want to get to. So, if 98% of the energy is in that one and 2% is in that one, it means we are trying to show that this one is much bigger than this one. How many times bigger? Well, let's imagine it was 50 and 50. Then we want to show they're the same. Let's imagine it's 33% and 66%. Then what do you want to show? that this one is twice that one there. So what about 2 and 98? Yeah.
49 times.
49 times. If that's 2% and if that's 98%, then this number should be 49 times bigger than this number. 49. Yes. You're checking how I got 49. Yeah? Let me see what you typed in to make sure. You
No.
No?
No.
No, show me.
No.
Don't be shy. No, alright, okay. What to say? Here. Look, if this was, I don't know, if this was 500 euros, yes, euros, and this here is 1,500 euros, then I want to show that this one is 3 times bigger than this one. It's 3 times bigger. So here in this example, if that's 2% and that's 98%, I want to check if this one is 49 times bigger. How did I get 49? How did I get 49? 98 over 2. Yeah. This is 49, isn't it?
It is. I'm just trying to, because the question doesn't explicitly tell us that it's 98. It's telling us to prove that it's more than 98.
Oh, okay. Well, what we'll do is we'll check, and we should, if we get an answer which is 49 times or more, is good for us then. So anyways, what we want to check what happens if I do a half 4 v2 squared over a half 2, 3, 4 v1 squared. What do we think this should equal? Should be equal to 49. That if I take this number and divide it by this number, it should be 49 times bigger. Now, Ugo and Who, what do we do next? You both told me what to do. Yeah, you can take this here and put it into that. But before I do that, let's simplify. M's gone, halves gone, so I have now 4 over 2, 3, 4, v2 over v1 squared. Let's see what that equals. Now v2 over v1, you can get that here, can't you? v2 over v1, what does that equal? 2, 3, 4 with a minus over 4. So this is, sorry, it's 2 over 1, isn't it? Yeah. Minus 2, 3, 4 over 4 squared times 4 over 2, 3, 4. What does that equal?
2, 3, 4, 4.
Give me the decimal, please.
Oh, I think it's 98.3.
Decimal, please.
98?
No, it has to be something in the 40s, I think.
Oh,
58?
yeah, it's $15.
Is it 58? Great! 58.5. We wanted it to be at least 49. So in fact it's much more. It's nearly 59 times bigger. No, it's not. It's not.
Because basically, like now, you multiply 49 by 2. Well, if it's lower, you still multiply times. So,
I think it would probably be something I don't know, like 0.75% and then 99.25% or something. You had it at 98.3%, but it was
99. Yeah, I had a 98.3.
yeah. So anyways, it's fine, because the question says, if you look here,
Sure, that's not.
show that it's more. So we want at least 49 times bigger. At least 49 times bigger. Now that was a difficult question for sure. That was difficult. But the problem is that it's an exam question. Those are questions I took from exams. That's bad news. Good news, I don't have any. I don't have good news. Sorry. What's that?
It's going to get worse.
Yeah, it won't get worse. Now, if I look at number 4, let's see, we're looking at time. Yeah, number 4, I really think that this could be done. In number 4, you have 2 pendulums. So this one falls down and hits into this one. So we say the kinetic, yeah, I'll draw it up here. Look. This falls down into this one here. What's the energy here? Not zero? Yeah, it's potential energy. And then when it's down here? Kinetic. And should they be equal? Yes. So then you find the V. You got the V, okay? Then when you get the V, what do we use here when it hits? What do we use when 2 things hit together? The conservation of momentum. And here what do we use? Conservation of energy. Now look, if we go back to the bullet, first we use conservation of momentum, and then for this part, conservation of energy. So for me, the only difference is the order. First we did conservation of energy, and then when they hit together, conservation of momentum. So I really think people could try and do this for me, and you know, I'm just looking at what happens in 4. I'm not
like the C part of this. I think you got MV.
Yes,
And just to see.
Oh, see. Ah, so you want a percentage loss. Yeah, so if you're not 100% clear, who's this? So Ibrahim, percentage loss. Percentage loss in kinetic energy. What you need to calculate is the kinetic energy before minus kinetic energy after over kinetic energy before multiplied 100. That's the loss in kinetic energy. If you use that formula, you'll be fine. Did you use that? No, so then this is the solution. Was there anything on the last page? What was the last page?
Was it for principal analysis?
No, I did do something else, didn't I? Oh, that was the last page. Are you sure? Oh, okay, working power. Oh, good, okay, so we did everything then. Okay. Right, we'll finish.